This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hello, I'm Lee Bortons, and it's Wednesday, November 11th, 2023. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss a math concept each week from our soon-to-be-released math curriculum for families with students in classical conversations communities. And soon is really soon. Friday is my deadline for it to go to the printer, so everyone pray. Kirsty, what do we have today?
Well, for those of you who were here last week and looked at the rate of change, this week hopefully is going to feel somewhat familiar to you, and at least in terms of the flow, and that is intentional. So we're going to be talking about accumulated change today. And so we have this great photograph, which in itself could be art, but also the arrangement of these rocks we could think of as being art created by the creator himself. And so we can talk about those, but I also love this quote by Leo Tolstoy, who said that yet in our world, everybody thinks of changing humanity and nobody thinks of changing himself. And so just a great reminder that we first need to be transformed, and then God can work through us to transform all else. So what do you guys think? What do you guys think of the rocks?
I know this sounds weird, but I every time I see this picture, I think it looks like wood, like pieces of wood, like a deck that's like falling apart. Like, I don't know, just the way the wood is laid, and well, I mean, it's not wood, it's rocks, but it just looks like old wood or wood that's been treated or something, like it's withering or something. I don't know. That makes sense.
I can see that.
I love that all the endings really help illustrate the idea that there's a curve, and then that there's ordinary shapes under the curves that are easy to calculate the quantity of them, say, and or the area of them, or even the volume if it was all three-dimensional.
It's a great point, Lee. If I was to find the volume of all of those individual pieces and add them together, would it be the same as the volume of the whole?
Yes.
Wouldn't it be like a Riemann sum where it may be?
Well, in this case, it would be, right? The parts equal the sum of the whole, or the sum of the parts equals the whole. And that may feel like an obvious idea, but it's really a big idea. It's one of those things that we just sort of take for granted. But it's actually a really big concept in mathematics. The idea that if I break things up into parts, that the sum of those parts has to be the whole.
Well, Jana knew that. She said yes.
Do you hear how confidently I said it?
Well, you doubted yourself because it seemed too obvious, right?
Yes.
You know, I just find it amazing that rocks can be in this shape and form because of a molecular structure that is followed. I just somehow that it comes to be a mountain and starts with a little molecule that's like, okay, we're going to connect these little pieces just right and form a crystal. And I'm astounded, to me, to be honest, that these don't look like rocks. These look like you said, like pieces of wood, that God would make that. I mean, that's so creative. So yeah, I just can't quite get past just that it's like this.
And there's a lot of formations across the world like this. It's not like they're unique in one area. It's a crystalline structure, like you said. There's a place near my home called Fairy Stone State Park where it does the same thing. It's a crystalline structure, but they all are in the shape of a cross, and to have a rock grow at 90-degree angles from each other is like, it seems even more miraculous. And that's why they call it Fairy Stone State Park. They say that when Christ died, the fairies cried and their teardrops turned into crosses. And so we went looking for them, thinking it was this great big geological expedition, when the kids were really little, and couldn't find them. And then so I stopped at this gas station and said, "Where are the fairy stones?" And he said, "Behind my shop." And you walk back there and they were everywhere. And so having eyes to see, it's like finding that first shark tooth. Once you find one, you see them everywhere.
I just think God doing things like this that seems out of ordinary. It seems against what rocks do, or even, over time, if this is standing up, if there's nothing to protect it from wind and rain, why haven't they dulled more than they have? Why don't they look more like a rounder rock? And then I also noticed, and it's just the timing of the picture, but the cloud is mimicking that right hand peak. And I just think that's really cool. It's like God's just showing off. It's like, hey, you're about to take a picture, watch this.
That's great.
I was going to say, it really looks like a cathedral to me. The way that the photographer chose to photograph it as well, from the perspective that he did. So it's just another spectacular showing of God's glory.
Just did parallel lines with my son. This is a good picture for that week too. Straight lines, intersecting line.
So why do you think we chose this? So look at the title, even if you don't know what this week is about at all. Accumulated change. What does accumulated mean? And why might we have chosen this picture to go with that?
Think of accumulated like gathering, and it looks like a gathering of these rocks.
It looks like they are also not necessarily gathering their growth at the same rate that some, they're different heights, and all of them together are beautiful.
When I hear the word accumulated, I think of snow. So we talk about snow accumulations. So to me, that's like packing on to packing on to packing on.
Can you accumulate in a negative direction? Like, could these have all been one height at one time, and then there was loss for some reason? Like, there's accumulation always positive? It seems like it's always positive to me, but I'm just wondering.
I'd never thought about that. In the context in which we're thinking of it, it's that idea of adding the pieces together, right? That I'm gathering or I'm adding. So if I'm going back to what we talked about earlier that you had the right answer for, right? If I add up all of these individual pieces, I get my whole.
But if you add a negative number, then you go the other direction, right? I mean, you can still add, but that's what we say in algebra. You add a negative. No, do we not say that?
Yeah,
well, I think of accumulated depreciation, which is actually like, adding to the loss of value of a property. So,
okay,
in that sense, yes.
All right. Well, I know we all like this part, but we must move on. So as we talk about language and order this week, I wanted to talk about the benefits of revisiting loci and topi. So I was trying to be clever, but what do those two words mean? First of all, right, before we can talk about it, we have to define our terms. So what are loci and topi?
Location and population.
You're close. So loci are locations, and that comes from Latin. Topi is Greek, and it is the plural for. Anybody want to take a stab?
Place,
right? Our topics, yeah, right. So our topos, our place. So it's the words that we're using when we think about. We talked about loci mathematically, we can describe locations. And then when we talk about our common topics, right, we talk about that topos, that idea of, right, these common places that we can go to. And classically, we revisit them, right? So the locations being our topics, right? We're revisiting these topics over and over again. And when I say topics, I mean our dimensional topics here, and then our common topics that we're revisiting over and over again, right? We're always coming back to these same 5 common topics. What are the benefits of revisiting those?
Revisiting anything in the
repetition. Go once. Go ahead, Bab. Sorry.
No, just the repetition, I mean, itself is beneficial.
Keep thinking of those rocks. You just keep getting more layers. And so you get this deeper, richer understanding every time you go back through. I mean, I always find I have resistance at the beginning because I don't understand, or I don't have my location, right? And then after time, as I get familiar with it, I'm more comfortable and I can start recognizing the details better. It starts coming together. So that to me is it. Yeah, I have to revisit. I'm not a really quick on the upstart, so it helps.
And don't we do that with scripture? You know, we reread a passage over and over again to get more understanding.
Yeah, I think your aha moments don't come on your first pass very often. So to, go through it more and more, and the more we know and the more other things we've learned, the more connections we make and the more ahas we have, and it sort of all comes alive.
Yeah, Lee was saying just yesterday, she said, any book you get, what do you first do? You kind of look at it and you sort of like how many chapters, and you just look at the big picture of the book, right? You familiarize yourself with the book itself. And then maybe you read it from the beginning to the end, right? You start and you keep reading. And then you come back and you're like, oh, wait, I want to revisit that. I want to, right? And so we everything that we do that matters to us, we do it repeatedly, right? We had a great conversation with the mentor tutors a couple of weeks ago about the art and the fact that we look at that art every year because the conversation is different every year. Right? If you think about your family meals, you don't go, oh, that was a really great meal. Too bad we already ate it. Never eating that again. Right? We have favorite family meals that we come back to because the next time we come back, right, maybe we're sharing them with different people, or maybe the conversation over the meal is different, or maybe the recipe changed just a little bit, right? Or we used our garden produce instead of grocery store produce, whatever it is, right? There's a value in coming back over and over again. And that's the same with mathematics, right? That as we come back and we look at these ideas over and over again, it's not a once and done, right? This first time through using the naturals, is that big picture look of just getting familiar. And then we're going to go through more slowly, and then more, right? And then we come back, oh, wait, what was that idea? I mean, I want to go back and revisit that. So, all right.
Just to give you guys some encouragement, I know I'm better at math than the average bear, mostly because I just always like puzzles and I like to be organized. But I got to tell you, this 5 years of just studying math so much, thinking about you guys and the children and tutors. But the bigger thing is just being under Kirsty's constant tutelage. I have learned so much, and it's such a privilege. And I just feel like the Lord has that in mind for many of us, not just, our team that did this. So I just really appreciate you guys being here over and over again.
Absolutely. I've learned so much because Lee pushes me. Well, why? Right? refine your answers, right? So it's that iron sharpening iron, right? As we talk, we realize the places where we took things for granted. Well, it's always been that way. Well, why? Well, let me sit down and figure that out. So it's been a blessing to be a part of this project, and And all of you guys every week are making it better. Okay, so let's jump in. And if you were here last week, it will be interesting to hear what is familiar to you.
Well, the lines down this, or the column down this side under function, those are the same words that we looked at last week. And I feel like I have a better understanding of what most of those are this week. Slightly familiar.
We recently did these functions, power functions, in the intersected lines booklet as well. So we have seen this. It's been a few weeks between then and now, but we could compare those exponents to the kind of function that we would expect to see, and recognize that even with the words, that we know that the 0, the 1, 2, those indices of 0, 1, 2, and then when they are fractional, that they kind of go along with the terms that we see to the left. So even if I didn't know what to do with that, those words and indices are familiar.
I just had an aha from listening at it 1,000 times. So the radical, I'm never going to forget that, because the radical is when you have the square root of something and it's known by 1/2. So of course that's called the radical, because there's a 1/2 there. That's okay if nobody else understands at all what I just said. I do.
No, I agree. When we were looking at it in class with the 12-year-olds, we just spent time looking at that, and they didn't have the 1/2 indices, but it did have the radical, square root box or other root box. So they could recognize, and you could cover up the word, and they could figure out quickly because of other things they knew. It was, I agree, wonderful.
Right. I'm going to see if it'll write for me. And I'm just going to, for those of you who are wondering, right, we have this written in one form. And here we go.
Wait, while Kirsty's writing it, that's one thing to watch out as you go through the charts. There's probably, I think there's 5 places where these equations are written, and they don't always look exactly the same because they're in the form you want for that kind of problem. So that would be something you could do one week, is just say, let's just look at all the charts with equations on it and see if we find the patterns.
Okay, so that -1, that's our rational. It makes our expression, and actually a rational expression, meaning it's a ratio. Then our radical would look like this. And so we have the radical sign. And then our rational radical puts both of those together. So those forms are equivalent. We just used, for the sake of space, but also for the sake of helping people to see the pattern, we chose to use the power form, which is where we have a base with an index, that power form, versus using the other symbols, just to help recognize that pattern. So I've heard from that the function name is familiar. The general equation is familiar. And some people are going, yes, this looks like a little bit of what we saw last week. Last week, if you remember, there was the rule was in the middle. And we heard you say that was kind of hard to follow. So we've moved the rule, and I just left it off for this week. So you can just see the function, the general equation, and then the integral. So I just want to say, we're listening to you when you give us feedback each week. We are growing and adapting thanks to you. So what is unfamiliar on this page?
So I'm seeing that on the integral side, where there's a lowercase on the left-hand side, there's an uppercase F on the right-hand side. And I'm wondering why.
Good question.
And I'm just noticing that integral symbol because we learned that one of the very first weeks of the math map with in the naturals. Like we just learned that that was called an integral, and my son's like, "What is that?" And I have no idea. I don't know, but we're just going to learn that that thing's called an integral. And so this is now the first time I'm seeing it. So it's familiar to me, and yet I have lots of questions about it.
Well, that's perfect, right? So the two things that you guys just said, right? I'm familiar with the lowercase f. I'm unfamiliar with the capital F. I'm familiar with the symbol, but I'm unfamiliar with how it's used. So that's how we build our knowledge, right? As we go, so here's something that's familiar. How do I make a connection to this thing that's unfamiliar? And so that lowercase f just says, this is my function of x, or whatever variable it was, right? So this is my function of x. My capital F says, this is my antiderivative or my integral of the function. And so that's what the capital F means. So if I see the capital letter corresponding to the lowercase letter in this way, it's saying you're looking for the integral or the antiderivative. And the integral symbol, right, is the symbol that tells us to actually integrate the function, right? And it says, okay, find the integral, integrate whatever it is that I'm telling you here. So that's what that, so now let's talk about integral and what other words does integral sound like?
Integrate.
Integrate and
Integer.
Integer.
Integrity.
Integrity.
Interval.
Okay, interval. So let's think about those words: integer, integrity, integral. What does it mean? Just in an English way. Don't think math. Just when you hear those words, what do they mean?
Something that's whole.
Injured.
Whole, right? So
It's
what this is saying is this integer symbol, which looks kind of like what letter?
An F. To me, it looks like an F.
It could look like a very old script F, or in our more modern alphabet, what does it look like?
An S.
Really
An S.
tall S.
Like a nice long S.
Or
So it does look like an S because S stands for sum. And so if I think of sum and then integer or integrate, right, I'm bringing things together and making a whole, right? And so the idea behind the integral is that I have lots of little pieces. So close your eyes and picture the photograph that's our art this week, right? Think about all the little pieces that make up that mountain, right? All of those columnar joints that make up that mountain, right? And now I add them all together and I get the whole mountain. That's what integration is. It says take lots of little parts and add them all together to get the whole. And that's all we're doing, is saying we're adding up these parts. So let's take a look at the pattern. And again, if you were here last week and got the pattern last week, and you heard me say that the capital F means antiderivative, right? You might notice there's a connection between our pattern last week and our pattern this week. So let's go ahead and look. The first one says the integral of 1 dx, which says the integral of 1 with respect to x equals x plus c. The next one is the integral of x dx, or the integral of x with respect to x, is x squared over 2 plus c. And then the integral of x squared dx equals x cubed over 3 plus c. And the integral of x cubed dx equals x to the fourth power of x over 4 plus c. And so let's take a look at the next one. And how would that one simplify? What's the integral of x to the fourth power of x dx?
X to the 5th over 5.
5 plus.
Yeah. So the
Is
fifth
there
power
supposed
of
to be a 4
x.
on the bottom?
Yes, there is supposed to be a 5 on the bottom. Thank you.
The other
There
one,
we
if
go.
you could look back to her integral of 1 dx, that could have been written as x to the first over 1. So help your kids fill in the hidden zeros and ones when we don't do it, or the problem does it. Because sometimes we don't have the space when we're doing a problem. We're trying to get them all in the charts.
All right. So how about the next one? How about the fifth power of x? What would the integral of the fifth power of x be?
X to the 6 divided by 6 plus C.
All right. So I've got 1, 6, c, and that becomes x to the 6th over 6 plus c. All right. And no help. How does what's the last one going to be? The seventh power of x? What's its integral? Sorry, the sixth power of x.
X to the 6 plus 1 over 7 plus C, which equals x to the 7th over 7 plus C.
Okay. So if you're not following the pattern, right, it's okay. But if you are, what is the pattern? How could you describe that pattern in a very general term? So for any n, for any exponent.
You're adding 1 to the exponent.
To the n
And then
plus 1.
underneath that n plus 1, it's the same. The n plus 1 is on the bottom, the denominator as well. Plus
Plus
C.
C.
Good. And now, because I said, right, this is the antiderivative, let's just take the derivative of one of these and see if we got what we started with, right? Can I undo it? So let's just say if I had x to the 7th over 7, and the derivative, if you remember, if I was to say, find the derivative of this, I would say my 7 comes down, right? So this becomes 7. I subtract 1, but I have to remember I'm dividing everything by 7. So what's 7 divided by 7?
1.
1. What's 7 minus 1?
6.
So I'm left with x to the 6. Is that what I started with? So
Yes.
it works. Now, does anybody notice anything that's on all of these integrals?
Plus C.
Plus C. Anybody want to take a stab at why it's a plus C?
Does it have to
Change.
do with, I think it's hidden zeros or other unknown whole numbers.
Right. So if I had said to you x to the 7th over 7 plus 5, and I asked you to take the derivative of this whole thing. What's the derivative of a constant? What's the derivative of 5? Anybody remember that from last week?
0.
0. Excellent. So this would be x to the 6th plus 0. If I had said this was 15, it would be x to the 6th plus 0. Right? So any constant here, when I take the derivative, gives me 0. So when I integrate, I want to say, hey, there might have been some whole number there that got lost when I found the derivative. So when I go backwards, that's what that plus C means. It just says, hey, there may have been a constant there. It might have been 0. It might have been 493 pi over E. Right? That's all that means.
So I'm noticing you have a capital C for that one. So like in the very first line, there's a lowercase c times x plus capital C. Is there a reason for that? Is that just the notation?
Where's that? Oh, yeah. So the lowercase c is just saying, hey, it equals some constant, right? So that was trying to say that we can write like y equals 5. We can write it in this general form where we have x minus h to the 0 plus k. But a lot of times, if you were to see this, people would just put y equals c, meaning it just equals some constant. But it's just any little, it just means it's any number. But that capital C is specifically called the constant of integration. Hence, it's a capital C. It has a really big name.
What is it? So when I'm looking at this, Kirsty, on the left column, general equation, you have your K, and I'm guessing that's the HK, meaning you've moved your point around from the origin. Yes. And then when I see the KX in the right column, that's the same thing. It's not saying K any constant, like, or a scalar. It's saying any transition you've made with the.
Yes, yes. That if that K had been a number, right? If I had because what we're doing here, let me just pull this. Let's see if I can make this work.
Because I was wondering, could that top line instead of CK plus C have been KX plus C?
Yes, it could.
Okay.
Well, no.
Because you mean any C, but K could be any K.
It could be, but we also would have, it would really be A plus K, because x minus h to the 0 is 1. So you have that A. Okay. And so it would be A plus K.
All right, I got off track, sorry.
So, yeah. So it's not quite as straightforward, because we have to take into account that there. Let me turn off my pen. I'm probably running out of time. I am running out of time. So I'm not going to explore the idea. I was just going to explore because we don't have time. Instead, we've shown this now for a few weeks about our release plan that is coming up and how excited we are for this. And I just wanted to pause for a moment and see if anybody has any questions about the release of the Math Map and how this might affect your family.
I guess I'm still, I have a lot of kids in high school right now that aren't going to get this. And I am planning to do the complex level with all of them next year. I think it's beneficial. I only have the one boy that's in A this year that will, he's still kind of missing it, but it's not really. But I've noticed such a difference. I mean, he's creating math problems for me with XY coordinates, and he's making connections. He has never done that. And this is after 10 weeks of the Math Map. I am so excited. But I feel like my high schoolers, they're not doing that, even though they're in, Algebra 2 and anyway, do you have any thoughts about that?
Well, I think it's a great idea to have all of them do the complex, because you're still going to be exposed, as you're seeing now, as you're getting into the 2D material, especially, you're still going to be exposed to all of these advanced concepts, right? They're still going to see algebra, geometry, trigonometry, calculus, matrices. So they're going to see some challenging things, even if they're not necessarily going to be going as in depth. They're still going to be exposed to a lot of ideas that they probably haven't seen yet, or they're going to have the chance to revisit them in context of the rest of math. So I think having them all start with complex, and then the next year everyone who's still at home can do monomials and get as much in as you can. I think of it like, I think it was Julie Melendez was my, I forget what they were called, but back when I was in SR, she was our sales manager, and she came and visited, and she just said, 1 year of challenge is better than no years of challenge, right? It doesn't really matter. If you just get 1 year in, do it. And so I feel the same way about the Math Map, right? So if you just get 1 year in, it's only going to help your students.
And even if they get into it, I feel like there's so much more that can be expounded from the charts, because the charts, there's so much more in the charts that they won't probably see in the pages because the charts are for all the levels. So I don't think this will happen, but if they got to a point where like I'm bored and I need more, they could always go to the charts. You know what I'm saying? Like I think people think that. They think, oh, I'm just doing this 7th grade curriculum, so my kid's going to get bored. Well, I don't think that's going to happen, but just in case, they can go to the charts, and there's so much more in the charts that you can use.
And Jill, you may want to jump in because I know that your sons have used this, even though they were not no longer in Challenge A.
Right. So when I started with the pilot, it was the first year of the pilot, and my youngest child was in Challenge A with me. And we have 2 girls and 2 boys. So the girls had graduated, but my older son was in Challenge 2. And we pulled him off of Saxon, and he did MathMap with us at home with my Challenge A student and with me. And we had the best conversations. It was the best math that we had ever done homeschooling because we could all do it together. And the things that my older son had already learned, he could help my younger son with. And the simplicity that my younger son saw some things helped my older son. And then we tried to go back to Saxon with my Challenge 2, and he could not stand it. After having worked with MathMap, that's really all he wanted to do. So we did MathMap, and we did some understanding mathematics. He worked through that book in a year along with MathMap, and he just stayed with MathMap through the rest of with the challenge. Complex was the highest we have, and so he kept repeating that and digging deeper and having richer conversations. And now my youngest is in Challenge 2, and he and I are still doing complex, but we're spending some of our time looking at the charts and doing what Kirsty affectionately, I believe, called plug and chug. So we're proving some of those formulas to ourselves by substituting some numbers into the charts. So I feel like my kids are having the best math that they've ever had, even though it's in some ways the most diverse and challenging math we've ever had with a parent who did not major in math. But for us all to work on it together and make those connections together, it's been amazing. So that's our testimony for it.
So one of the questions that I've had is, so I would agree with kind of like the olders. I can really see how that would work well to continue with complex. But one of the questions that we're having now is with the youngers who want to get on board. And the question is, okay, so if we start with fractions or we start with naturals, is it enough to just do that? Or do I need to continue that like as a supplement with my normal one? Because they don't have access to the charts. They don't have access to the companion for that level, if I'm understanding that right. So will the parent have enough support to do just that?
So they will have.
Kirsty, let me answer that a different way. So 10 years ago, I was giving a math practicum long before this was even in my head. And a math professor was in the room, and I knew that's what he was. And when I was all done making some comments about what curriculum should be like, he raised his hand, and I just thought, oh no, I'm in trouble. And he stood up and he said, look, this is all really great, but I'm a college professor of mathematics. Could you just please teach your children to add fractions? And that was 10 years ago. So we have high ideals and not really enough practical on the basics. And the flashcards are the most important thing, not the curriculum, and getting those facts down, no matter what age you are. And now you answer it, Kirsty.
Sure. So I was going to say, one, when the companion is released in the spring, everybody will have access to all of it, with the exception of the things that are specific to tutors, right? There's a very small piece of it that is specific to tutors, and that's there for tutors. But all families will have access to everything that we've released. Now, understand, this is a mammoth task, the curriculum, and the companion is in some respects even more mammoth. And so there's pieces of it, right, that are going to roll out over the next multiple years. So next year we're going to have a lot of detail for the complex years. So other parents that are looking for more information may have to go and look at complex and go, okay, well, what's there that I can glean, because we haven't rolled it out to them. But remember, all of these things repeat every year. So if I had an 8-year-old next year and I said, okay, we're going to do the naturals this year, and that's all we did. I didn't have another math curriculum. I did the naturals with them that year. I've just given them a good introduction, right? If you've been using the naturals, that's what we've been doing this book club on. We go, okay, this was a good introduction, but there's a lot we haven't done. Well, the next year I'm going to come back and I'm going to do fractions, right? Because now my child is 9. So I'm going to jump in and I'm going to do fractions. And in that fractions booklet, I'm going to practice fractions. I'm going to practice decimals. So I didn't really lose out, right? I'm not going to have that solid year of practice, but I'm still going to have the opportunity to operate with decimals. I'm going to have the opportunity to operate with integers. So in that fractions year, I'm going to see all of those sets that are to the left. Then the next year, I'm going to be able to just follow through and go fractions, rationals, reals, and into complex. If I'm 9, 10, or 11 next year and I just have 1 year fractions, it's still going to be a great preparation for going into complex. So yes, if somebody next year just has 1 year to prepare for complex, it will be enough. In 10 years time, when kids have started with digits and they get to complex, are they right? It's just like anybody who does like my daughter did 8 years of foundations, right? Did she had more repetition, so did she perhaps have more of that in her memoria than somebody who just did 1 year or one set of cycles? Yes, but whether they have 1 year of foundations or 8 years of foundations, they're still prepared for challenge and complex. So does that answer that question? Does that help?
That does help, but you said getting the charts or whatever from complex, they won't have that unless they buy it.
They'll be able to see it online in the companion. They won't have physical copies, but they'll be able to see all of that online in the companion.
But the chart, they can do it effectively without the charts.
You really can. The charts are there. So the charts have 2 purposes. One, the chart is, when we talk about mapping mathematics, we have that sort of zoomed out map that says, here's your lesson, your topics, your dimensions, and here's your domains, and this is your journey through. And then, if you were to come to North Carolina, you might have looked at the big map, and then you get to Moore County and you want to come and visit us at the Math Map offices, you're going to get a more detailed map, right? That's got all the street names and maybe some landmarks. That's what the charts are like. They're like your inset map or your detailed map for addition or for derivatives or for integrals. So as for a parent of younger students, it's really there so you can go, why is my kid doing this, right? Why did we need to know what an integral sign was? Well, if you look at the chart, you go, oh, that's where it fits in, right? That's where this idea fits in to this whole. And I also see what's my goal by the time we finish at challenge 4, right? I can see a detailed map for this topic over 13, right? To that 13-year goal. It's also a reference, right? So if you sit there and you're like, well, wait a minute, what was that formula? Those things are all on those charts. So they become a reference. But really, for those younger students, the charts are there more for the parents, more to give them that big picture of what they're doing. And there's going to be less need to rely on those for a reference. But anybody who does want to refer to those until those printed versions are available will be able to see them online.
Okay, great. Thank you so much.
You're welcome. All right. Well, I know we're kind of out of time, so I'm going to briefly just pull up this next slide and just ask you, right? Look at this image. What are 2 ways you could calculate the area for that shaded area?
You could count it.
Excellent. You could count, right? Any of us could count that. What is the other way we could find the area?
the formula for a triangle.
The formula for a triangle. Excellent. And now I have to remember, what did I say to click on? Yes. Okay. Now look at this image. Okay. Can I use a triangle?
You could
No.
estimate using a triangle.
I could estimate using a triangle. Could I count?
Not.
It's gonna be an estimation still.
It's still going to be an estimation. So let's look at that. If I used a triangle and right, and that, so here's my 2. Hang on. I messed up. Let me pull my pen up. All right. So this is my X. I don't know if you can see the red. Here's my X. This is my F of X. All right, here's my X. This is my F of X, which we're doing X squared. So this would be X squared. So if I was to do my 1/2 base times height, I would have X times X squared over 2, right? For that triangle. Is my area more or less than that?
Less than.
Less.
Less than. And in fact, it's going to be X squared, X cubed over 3, right? So this is X cubed over 2. Is X cubed over 3 less than that?
Yes.
Yes, right? So that gives you this very gentle hint of where this integral is coming from, right? But it's different. So I'm going to show you one more picture to turn off the pen, and then I can click. And now look at this image. Do these rectangles, right? So here's a rectangle. Imagine there's a line here, right? Do they remind you of that picture on the cover?
Yes.
Oh, yeah.
Yeah, right.
They do.
So if I added up the area of those rectangles, would I have an estimate of the area under the curve?
Yes.
Yeah. What if I made them thinner? What if I said, let's look at this rectangle and then this rectangle and then this one, and then this one, and then this one, right? If I made these rectangles thinner, would I get a better approximation?
Yes.
Yes.
And right, so if I keep making them thinner, I'm going to get a better and better and better approximation. That's the
Yes.
idea of an integral, is I'm slicing now. And so what I eventually end up with is are an infinite number of slices. And when I add them all together, I get the whole. Right? And that's all integration is. And if you think about integration in the 1960s and 70s, what did it say? It said, like, we're going to take everybody and we're going to bring them together to make a whole. That's all we're doing here, is we're taking all of these pieces and bringing them together to make a whole. So that was really a quick view of that, but that does complete our time in the 4th dimension. Next week, look at that. We're going to ND. We're going to be using our imaginations in N space and talking about complex numbers. This is exciting and sad all at the same time, because there's only 4 weeks left. But I hope you all have a blessed week until then, and I look forward to meeting with you next Wednesday.
Thank you.
Thank you. See everybody next week.